Hi, class. As we discussed last week, many of you expressed an interest in working with survey data, particularly survey data that might be relevant in the context of, say, doing a chart analysis. And so today I'm doing a supplemental exercise that we'll work on a little bit during tomorrow's class that will teach you some of the important skills in survey analysis. Now, the first thing that I wanted to tell you about, we're going to go through the example data of one of these projects. And what we're going to be working with is a medical instrument I know fairly well, and that is the Epworth Sleepiness Scale. A little bit about the Epworth Sleepiness Scale. That's often used as a precursor in sleep studies. And the thing that's really nice is it's very interpretable. What it is basically you ask people a list of questions of how likely they are to fall asleep in certain activities, and then based on that, your score, you will be diagnosed with as falling into one of the following buckets. That is, 0 to 5 is traditionally considered no sleepiness. 6 to 10 is sort of higher. But typically for medical diagnostic purposes, particularly for sleep apnea and those things, 15 and above is usually considered the cut point. And just to look, I'd really encourage you to take some time to look at the rest of this website, and I'll be posting a link to it in the tiny URL. Is that it covers a lot of the questions and concerns that one might have when designing a good survey. So just looking at some of the items, you can see that they're largely fairly interpretable. And what these questions are is just, again, it's asking you how likely you are to fall asleep during certain activities. And they're all pretty intuitive: sitting and reading, watching TV, sitting inactively. And most of those are everyday activities, and then there are ones that are a little bit more severe in terms of potentially being a warning sign of something more serious going on, in particular, being highly likely to fall asleep in a car while stopped for a few minutes. In terms of the other sort of intake factors that the Epworth Sleepiness Scale uses, it uses age and gender, albeit, as you note here, that's not part of the diagnostic in terms of calculating cut scores. So the other things that I want you to take away here is that, again, a sleepiness score greater than 15 is likely to indicate that you might have sleep apnea or another sleep disorder. The other thing that I want you to read about is that there are these psychometric measures of how good of an instrument it is. And there's this concept called Cronbach's alpha. And the way I like to describe Cronbach's alpha is it's a measure of how closely one item is correlated with another. And it's a little bit more complicated than that. But what you like to see is that ideally, if you were to take, say, odd responses and even responses of a survey within users, so for example, if I showed you the odd items here and the even items here, so for example, the odd numbers would be sitting and reading, sitting inactive in a public place, lying down to rest in the afternoon, and sitting quietly after lunch without alcohol, and then measure the sort of sum scores and the correlation between watching TV as a passenger in a car, sitting and talking to someone, and then in a car while stopped for a few minutes. Ideally, if we think we're measuring something that has an underlying construct, this sort of like random ordering of the items would still result in the even numbers being fairly correlated with the odd numbers. And the way we calculate that in a generalizable form is this thing we're referring to as Cronbach's alpha. So That being said, let's take a look at our sleepiness data real quick. And where this information is stored is at tinyurl.com 401A week 2. Right? So what we're going to do is we're going to open up the demo data real quick. And actually, let's go to the virtual machine for this. So we're going to do the same thing. We're going to go to our tiny URL. And let's take a look at the way our data is structured. So in fact, let's open up the .save files. Sorry, this is taking a while. And I know it's frustrating that the virtual desktop sometimes will misbehave in this fashion. So I'm going to pause it real quick and hopefully it will load by the time we're ready to resume. All right, so we are going to look at this data in PSPP because SPSS is misbehaving itself. So what we're going to do is we're going to look at that same sort of sleep apnea data set that I told you about earlier, except we are not going to receive it all at once. We are going to have a merged version of this data set that we're going to have to make. And it's going to come in two pieces. There's going to be a survey data component and a demographic data component. So let's first take a look at the survey data. And as we see here, that we've got our individual survey measures 1 through 7. So there actually is a variant of this sleep apnea data set that only used 7 items, but it's quite similar. And then our 8th indicator is a patient ID. And let's take a look at our data for a second. Things I want you to know about this data set is that we have exactly 100 patients. And the reason we know that is the patient IDs are labeled 1 to 100. But then when we scroll down, we see that we have more. So one of the things I did was I added duplicates into this data. And what we're going to do is figure out how we can handle duplicates in our analysis. And on the left-hand side, we also have our survey responses. So again, this is just how likely you are to fall asleep under certain circumstances. And one of the things I also want you to notice here is that there are missing data. And in this particular instance, I decided that there should be about 1% missingness in this type of data. Okay? So the next step is figuring out how are we going to deal with these duplicates. So dealing with these duplicates, there are a couple of ways we can handle it. One of the easiest approaches is just to sort based on a particular case. So we've got our patient ID. And what this does is it made it really easy for us to identify where we have duplicate values. And one way we could go about this is, you can imagine, we could individually delete these duplicate values. But that probably doesn't make a whole ton of sense in this fact that it's a lot of manual deleting and pointing and clicking. So let's think about, is there a way to do this with, say, descriptive statistics? All right, so we've got it up and running in SPSS now. And so let's load the survey data that I showed you in PSPP, because it's a little bit easier to handle these duplicates here. All right, so what we're trying to do is, we know we have duplicates, and we're trying to figure out what's the best way to get rid of them. And we can count and delete the 20 or so, and we know that there should be at most 100 observations, and we have 120. So there are a couple of ways we can do this. I think one of the easiest ones is to go down and scroll to identify duplicate cases. And what we want to do is define matching cases by patient ID, because we know that should be the primary identifier. And what it's then going to do is generate this variable called indicator of primary cases, where 1 indicates that it's a unique value and 0 indicates that it's a duplicate. So we're going to do that. And as always, I encourage you, if you want to understand the syntax of these commands, we can use the paste command to sort of see how that populates in a window. And as you can see, that there's a lot of code for what feels to be a fairly simple command. So I alternate on whether or not you should really use SPSS syntax from scratch. I think it's really important to generate a syntax file, but you don't necessarily need to know how to write all of these commands from scratch when you're doing your analysis. That being said, let's get back to it. So we've got our survey data. We want to go down and identify our duplicate cases. So we've got our patient ID and as our matching case. We generate that. As I told you, that we have 20 duplicate cases. All right. And now when we go back to our data window, what does that look like? We go back to our data editor. We have this new flag, primary last. And as I said before, zeros are duplicates and ones are either a unique value or the last value. So what we're going to do is we're going to sort it. And there are a couple of different ways you can sort. I like to do that from the column level. So we're going to click sort ascending, and we scroll down. And that we see we have exactly 20 duplicates at the top. And what we're going to do is we're going to right click and we're going to clear. Okay. We're going to right click, we're going to scroll all the way to the left, and then we're going to clear. we're going to press delete. There we go. And we have exactly 100 values now. Perfect. And now we're going to do some descriptives of the actual survey data. So as I said, one of the things that is really useful to do in terms of assessing the validity of an indicator is to compute this measure called Cronbach's alpha. And so what we're going to do is we're going to go down to analyze. And the way it takes a little bit of time to understand the reliability, what type of, where everything lives, but computing Cronbach's alpha, we're going to go down to analyze, then scale, then reliability analysis. All right. And here we're telling it which of these items are part of our survey measures. And as I told you, V1 through V7 are going to be the survey responses. All right. And there are a few different variants I've told you about. So split half is evens and odd correlation I told you about. But primarily what you're going to do is you're going to do this alpha, which is the Cronbach's alpha we talked about. All right. So we're going to press OK. And and we've got our Cronbach's alpha with around 0.82. And we also note that there are some values that were excluded from our analysis. And why is that the case? Well, what is going on is when SPSS is doing its analysis, it's not quite sure how to handle missing values. So one of the things that individuals often, one of the things that your program will often do is engage in something called list-wise deletion, meaning that if there is any missing data in a given row, then it's not going to include that example in the analysis. And I want to take a moment here to clarify that that different fields have different approaches with how you should deal with missing values. In psychology and in the medical industry, imputation, meaning trying to figure out what those missing values should be and then filling them in, is quite common. In economics and in other fields, there's a much higher propensity to just do list-wise deletion. Neither approach is wrong, but it's always important to communicate with your audience what you're doing. And so, and in fact, if you want to look into how one can replace missing values, you can go to transform. And one thing that you could do is you could assign the mean, which is quite common. Then there are other methods that potentially do some sort of interpolation based on values where you did have reporting. So that is sort of what the mean of nearby points are. And the median of nearby points is similar. And again, all of these can be quite reasonable depending on the context. But in general, I'm of the attitude that unless you have a ton of missing data, that list-wise deletion is not a bad place to start. Okay. And now what we're going to do is we are going to look at that demographic data. So we're going to open up that. All right. And here we have, let's see, 1, 2, 3, 4, 5, 6 fields. And on the leftmost column, we have something that's called the sum score. And you remember earlier in this video where I showed you the Epworth Sleepiness Scale, and individuals who had scores above 15 are considered to suffer from a sleep disorder. So that's exactly what this sort of sum score variable is. Okay, and then we've got our patient ID file. We've got a completely random number that I generated out of nothing. Then we have other patient information, that we have how many sleep apneas they had per hour. This is a measure called the AHI. That's the apneas per hour index. And then we have the BMI, which is the body mass index. And one of the things that we're going to look at is whether or not there's any associated correlation between, say, being overweight and having a high AHI. And finally, we also have demographic characteristics such as gender. And we're going to look at how we can factor in that analysis and perhaps do some plots by gender to see if there are any differences. So first things first, we know we have duplicate data in our survey data. Let's check and see if we have our duplicates in our demographic data. And it turns out we do. We should have at most 100 patients, and we have 120 observations. So we need to do the same thing. So get rid of duplicates. So how do we do that? Well, we identify duplicate cases. We select patient ID as our key. All right. We identified our duplicate cases, and we're going to sort based on variables. Oh. We're going to sort on cases. And then we're going to go down to that indirect indicator of whether or not you're a primary key. And we sort based off of that. And we see that we've got that same 20 cases. And what we're going to do is we're going to scroll up and just press delete. Perfect. So now the tricky part. We've got to merge our data sets. And we've got two choices. So we go to data, and we scroll down to merge files. And there are adding cases, which make your data longer. So you'd use that in case of, say, I told you we had an additional 200 patients we wanted to look at who also filled out the survey. And we're not going to do that today. But we are going to focus on is adding variables. And the way we do that is we go to merge file. We click add variable. We click on our survey data, and then it's going to prompt us what we should merge on. And there are a couple of different options it presents us with. One is a one-to-one merge based on file order. I really don't recommend that you do this under any circumstances. It's really easy to accidentally merge based on file order, and someone will unknowingly sort the data and not tell you. So I really don't recommend you do that. What is a good option is doing a one-to-one merge based on key values. And that just means you make sure that you have the same identifier in your survey data and the same identifier in your demographic data. And then we'll just sort of add them horizontally the same way you would if you were copying and pasting them from an Excel file using VLOOKUPs. And then finally, there's a one-to-many merge based on key values, and you'd want to use that in cases where, say, there were hospital codes that would apply to many patients. And that's one of those cases where you'd like to do a one-to-many join, where you have, say, 5 or 6 hospital codes to hundreds of thousands of patients, and you wanted to say, identify these individuals had heart attacks, these individuals had say, food poisoning, and other considerations like that. And finally, we need to select our key variables. So one of the nice things about SPSS is it's pretty smart in this respect, that patient ID and that sort of primary last indicator are the 2 overlapping variables in our data, and it sort of assumes that's what we're going to be merging on. This isn't necessarily always the case, but I'd say it's good practice to use similar names for the variables you're merging on. Okay? And we actually only need patient ID because that's what we call a primary key. That is something where we've already duplicated and know that there's a unique value for each patient ID for every observation in the data set. So we're now going to press OK. And again, one of the things I always encourage you to do is look at this paste command to see how it's being done. And we'll do that real quick just for completeness. Okay, let's go to our syntax window. And what does that look like? So when we generate the syntax window, generate the syntax for merge, what it does is it activates both data sets, sorts by our primary keys, and then we match files, and then we join based on these keys. Perfect. All right, let's do that with the GUI. So we're merging files. We go to add variables. Click on our open dataset. We continue. We press OK. And perfect. We have all of our sum scores. We've got our patient demographics, and we also have our survey responses. So one of the things that I find really helpful when I'm doing sort of survey analysis or just doing any sort of merge is just make sure that the number I have before and after a merge makes sense to me. And so here we had 100 observations in both data sets, and we still have 100 observations in the combined data sets, which sort of suggests we're in good shape. Now, there are a couple of things we can do here. One of the things that is, when we're doing survey analysis, that I find to be quite useful is to sort of see how each item response correlates with the sum score. And what we can do is we can go to the descriptive statistics. Correlate. So what we can do is we can take, say, sum score, and then what was our V1 measure of sleepiness? Let's see, let's go back to the Epworth. Let's go back to the Epworth sleepiness score real quick. And just so we have a concrete example, looking at V1, what we see is that how likely am I to fall asleep while sitting and reading? So what we're going to do, we go through and look at the correlation coefficient between the two of them. And we are selecting a Pearson correlation coefficient. That's typically the most common one would compute. And then we also want to get statistical significance. And we wanted to make this as easy as possible for us to recognize if there's statistical significance is present. Okay. All right. And so what we see here is that, in fact, this one indicator only has a very weak correlation. That's only 0.013, meaning that there's a very slight positive correlation that as the value for V1 goes up, that the value for the sum score goes up. Now, let's check this out with another feature. So again, let's take a look at the correlation between, say, the sum score and the how many sleep apneas one has per hour. So we're going to remove our V1, and we're going to add AHI. And now we're going to compute it again. And here we actually see a much stronger correlation coefficient. That on average it's around 0.587, which is somewhere between a moderate and a strong correlation coefficient. And what that says is that as the number of apneas you have per hour goes up, so does your score on the Epworth sleepiness scale, and vice versa. All right. Well, let's see if we can do some fancy graphs as well. So, well, actually, let's do one more correlation coefficient. I told you that this random number is a completely random number. So what we would expect is that when we do our correlation coefficient, with a random number, that it should be 0 or very close to 0. And that's largely what we see, is that there's no significance being flagged, and that the random number correlation between apneas and the random number itself is relatively close to 0. So all of that is pretty consistent. Now let's do some plotting. And what I think is, I think what we're going to focus on is bivariate plots today. That being said, one of the things that I've forgotten to do that is always important, and I highly recommend you do after you do your merges, and just whenever you open up a brand new data set, is to do some basic descriptives. And let's do that for all of our values. Okay. And again, this was a nice check on what we were thinking, that our sleep apnea, or our sum score should be somewhere between 0 and 24. And in fact, we're pretty close. It's somewhere between 1 and 19. Again, this is a slightly different version of the instrument. So there are 7 items instead of 8. So the max score was only 21. Then we've got our patient ID. Again, we sort of see that it goes from 1 to 100. And that sort of indicates that we are likely dealing with, it's not a guarantee that we have unique data, but if we saw something other than this and 100 observations, we know we were missing potential data or we had duplicates. And then we sort of see the performance of sleep apnea, and ranging anywhere between 6 per hour to 60 per hour. And again, these numbers aren't crazy, particularly for people who have sleep disorders. And then we look at BMI, and BMI looks a little bit weird to me. And part of the reason why it looks weird is I generated synthetic data to make this feel a little bit more realistic, a little bit closer to the results that I wanted you to find. And here, the things that would throw me is that BMI typically, if you're below 15, you are severely underweight. And here, our lowest value is 3.76. So one of the things I would do when I see something like this is make sure that I had my units in place. So for instance, I didn't accidentally interpret someone's weight in kilograms and then assume that they were pounds. So that's somewhere I could imagine a mistake like this occurring. And then finally, we have our survey responses, and you can see which ones had missing values and which ones did not. Perfect. So then, let's see. Let's do some plotting. Now, one thing that I always find very helpful is scatter plots, just to, even though we saw that there was a correlation between sum score and AHI, it's always useful if we can visualize them. So what we're going to do is we're going to go to a scatter plot. And on our x-axis, we're going to have our sum score. And our y, we're going to have our AHI. Okay, let's take a look at this. We run our chart builder, and we see that there's a pretty good horizontal 45-degree line here. That it's a little bit noisy, but generally as one goes up, the other tends to go up, which is interesting. It's something that we would expect, that as you exhibit more sleepiness according to the survey, you might have more sleep-related problems with regards to your breathing. All right. And now let's break this down by one other feature. We have this gender variable. Let's see if we can plot AHI and sum score and gender all at once. And it turns out we can't. These things aren't necessarily the most obvious in terms of where they're living. So let's go to it again. So we drag, and then we put our indicator for gender as color. And here we have our females in blue and our men in red. And again, one of the things that should stand out from here is that women generally seem to have lower sum scores than men. And in fact, what we see is that there's a sharp dividing line at around 12 or 13, where there are no women who have scores of 13 or higher, and there are no scores where there are no men who have scores of 13 or lower. So again, this is artificially created data, but I just want a really sharp visual that you can see. And so one of the things that I naturally want to ask now is, do men and women score about the same on this sort of test? And there are a couple of ways we can look at it. But here we're going to use a statistical test. And let's see. So we're going to go down to compare means. And what we're going to do is we're going to do an independent sample t-test. And what independent sample t-tests mean we are going to test by group, but this isn't like a paired t-test where, for instance, you might be interested in sort of, say, a pre-post gain, or you might be interested in the relative difference between two variables that are related. So for instance, someone's height and weight. So we figure out our variable of interest, which in this case is going to be our sum score. And then we are going to go to our grouping variable, which is the male indicator. And we're having issues. Why are we having issues? Oh. Can try telling it that these are we need to define our groups, and let's see if that does it for us. And what this does is it generates our t-test, and we see the mean by groups. So we see that men on average have a sum score of around 15 on this sleepiness scale, and women have an average of around 9. And we have these things called statistical significant tests. And we see that there's this is a really large difference. So typically, the thing you want to look at is this sort of significant coefficient, or a p-value. And if it's less than 0.1 or 0.05, it's typically considered statistically significant. Another way you can look at this is by looking at a confidence interval. And if 0 is within the confidence interval, it's considered not statistically significant. Again, this all varies based on features like what sort of confidence interval you use, and these are all parameters you can manipulate. And before we are all finished, there are just 1 or 2 more things I want to show you, and I know this is a lot, so don't stress out about this. You aren't going to have to do this as part of your homework. But I really wanted to make sure we covered survey analysis. Is that one way you can also sort of look at how items perform are to do something called factor analysis. And what factor analysis is a way of sort of decomposing items into their perpendicular components. So the same way that if I were on the XY plane, I could tell you exactly where you are by going up or down or left or right. That is exactly what principal components analysis or factor analysis does, is it decomposes into these orthonormal or perpendicular directions, so you can figure out which items or which sort of dimensions of interest explain most of the variance. And what I'm looking for here is just to give you a visual of how a principal components analysis or factor analysis looks, is we're going to look at something called a scree plot, and that sort of tells us how much variance we're explaining by incorporating each additional component. So we're going to generate that. And we're going to scroll down, and what we see is that incorporating the first factor explains a large deal of the variance, but then when we start including additional vectors, the gains tend to sort of drop off pretty quickly. So if you wanted to have a quick 1-number summary, looking at, say, the first principal component makes a lot of sense. In terms of general practice, people will incorporate varying degrees of principal components depending on what their goals are. Some might say that I want to incorporate 95% of the variance. So in that case, you'd say incorporate 6 principal components in your analysis. Others might say I just want to explain 70 or 80, and then you might only choose 4 or 5. Again, it all depends on the context, but this is another way of making sure that your survey measures are correlated in a fashion that makes sense for you. And then finally, I know we're dragging on a bit, so we're just going to do one more plot. And we did box plots last week, so we're going to do one more type of box plot. And this is, again, we wanted to visualize that difference by gender on the sum score variable. So we're going to go to box plot. And on the one hand, we've got sum score, and the other, we've got our male variable. Let's take a look. What does it look like? And you can see that it's exactly like our summary statistics, that our male students, or our male patients, have a higher sum score on the sleepiness measure than our female patients. And that's it. Thank you so much for bearing with me. You've done a great job, and I look forward to seeing you tomorrow. Take care.